Hey everyone. So in order to help a little bit with the reading for this week, I thought I would do what I initially thought was going to be a brief intro to simplicial sets. So I should say there's 100 simplicial set intros out there. They're really easy to find. But I thought I would just do one, keeping in mind the content that we specifically need for our paper. And in case some of you already have some background on simplicial sets, when I share this on Zulip, I will tell you where you want to jump in this video if you want to go ahead and skip the definition and go straight to the juicy stuff. All right, but let's start with the basics. So simplicial sets are a type of structure that comes up a lot when we do homotopy theory. And it also comes up when we study higher categories like we're doing this week in the paper. So what is a simplicial set exactly? Well, here's the concrete definition. A simplicial set is a collection of sets. So we have one set for each natural number, and we're counting 0 as part of the natural numbers here. And we also need some collections of functions. So we want a function di from xn to xn minus 1 for each I between 0 and n. And we also want a function si from xn to xn plus 1 for each I. And note that the di's are going down in dimension and the si's are going up. And then we need these di's and si's to interact with each other in very specific ways as given by these equations right here. And that's it. That's really formally all that a simplicial set is. Now, of course, if this is the first time that you're seeing this doesn't really tell you much. So let me tell you how we like to look at simplicial sets. So remember, we have a collection of sets xn, one for each n, and we're going to call the elements of the set xn n simplices. And the idea is that we're going to picture these n simplices, which a priori are just elements in an abstract set, but we want to picture them as n-dimensional triangles. And at this point, you might be wondering, why the heck would I do this? But more on this later. For now, believe me that we really want to do this. And so from this perspective, x0 will be the set of 0-dimensional triangles, which we just say these are vertices. x1, we have 1-dimensional triangles, which are segments. For n equals 2, we're going to have 2-dimensional triangles. These are actual triangles. For n equals 3, we're going to have tetrahedra, and then higher dimensions, which I'm completely unable to picture here. But you get what I mean. Note that all these are numbered. So all the vertices here, we're going to keep a numbering on them. All right, so this is how we're going to picture the elements of these sets. And now for the functions, we're going to call the functions di the face maps. And the idea here, if we keep our triangle intuition, is that the map di is going to pick out the face of the triangle that does not contain the vertex I. So let's do some examples. Let's say we pick the map d0 from x1 to x0. So remember, x1s are intervals, x0 are vertices. So d0 is going to grab this interval right here, and it's going to pick out the vertex that does not contain 0. So that's 1, right? It picks out 1 right here. That's the vertex that we get. Let's do one more example. Let's say we consider d2 from x3 to x2. And remember, like here, I should be saying so this is the I. When I say d2, this is I equals 2. And this is the n, right? Let's scroll up a little bit. We have a di and an si for each n, and we're kind of omitting the n notation because we're writing the domains of the function. So it's kind of obvious here who the n is. All right, so here we have a D2 from x3 to x2, and x3 are tetrahedra. So this is going to grab our tetrahedra and pick out the face that does not contain the vertex 2. So look, if you look at the picture, it picks out the back face of the tetrahedra, which is the triangle with the vertices 0, 1, and 3. Okay, so the DIs are the face maps, and the SIs are what we call the degeneracy maps. And the idea is that these are going to create a degenerate n+1 simplex from an n simplex by duplicating faces in the places I and I+1. So what does this mean? This really becomes a lot clearer with an example. Let's say we take the degeneracy map S0 from x0 to x1. X0 are vertices, so we take a vertex here, and we need to create an interval from this vertex. And what we're going to do is create a degenerate interval that is kind of a line that goes from 0 to 0. So it's degenerate in the sense that we formally need to have an interval, but it's like nothing is really happening here. There's nothing interesting that's being created, just duplicating information. To see a higher dimensional example, let's say that we want to look at the map S1 from x2 to x3. This is going to take a triangle in x2, and it's going to create a tetrahedra with duplicate faces in the faces I and I+1. So that will be 1 and 2. So let me just draw a little picture here. Let's say that we have a tetrahedron 0, 1, 2, and 3. What is the D1? What is the one face? The one face is the one that doesn't contain the vertex 1. So it's this one on the bottom, having 0, 3, and 2. What is the 2 face? It's the one that doesn't contain 2. So it's 0, 1, and 3. It's the one in the back. Okay, so our degeneracy map S1 is going to create a tetrahedra such that what we see here as the blue face and the red face, so the one face and the 2 face of our tetrahedra, have to agree with the triangle that we start with. And this is the tetrahedra that you get over here. It has vertices 0, 1, 1, and 2 because it duplicates. So the idea with these degeneracies, I know that they're a little bit harder to understand than the faces, but the idea is that when you create a degeneracy simplex, it should be such that if you pinch the segment that connects the repeated vertex, you should recover the lower dimensional simplex that you started with. So here you'll be pinching along here, and in the tetrahedra example, you will be pinching along the vertex that joins 1 and 1. So imagine just collapsing that down and you recover the triangle. All right. So this is kind of the way that we think of the data, so of the sequence of sets and the sequences of morphisms. But what do the equations mean? Why are we requiring all of these relations between the faces and degeneracies? Well, let's look at the first one, which was di dj equals dj minus 1 di for I smaller than j. Let's do a toy example where we take n equals 3, I equals 1, and j equals 2. Okay, so in this case, what we're going to do, we're going to go from x3 to x2. We're first going to do dj, which is d2. Then we're going to go to x1 by doing di, which is d1. So this is the composite on the left in our equation. And then we want to go to x2 by first doing di, which is d1, and then by doing dj minus 1, which is d1, and we want to see that we get the same thing at the end. So let's run these for an object. So we have a 3 simplex, which is a tetrahedra, like this, 0, 1, 2, 3. If we first do D2, we recover the face that does not contain the vertex 2. So we get the triangle 0, 1, 3. And then we take the face D1 that doesn't contain the vertex 1, and we end up with the interval from 0 to 3. If we run it the other way around, and we first do D1, we get the triangle that does not contain the vertex 1, so the triangle at the bottom, 0, 2, 3. And then we want to do D1 of this. Now, since we haven't numbered 0, 2, 3, I know that we don't technically have a 1, but if we look at these as ordered, we would say, okay, 0 is the first one, and then the next smaller number that we see is 2, so we're going to take that as our relabeled 1. And the next vertex is 3, which we're going to relabel as 2. So the important thing is that we need to keep the order, and the D1 means if we have 3, just take the middle one. So if we take the face that does not contain the middle one, which is 2 in this case, we get the segment from 0 to 3, and we see that these two obviously agree. So at the end of the day, this first equation is telling us that the two-dimensional faces are glued along a common one-dimensional face, meaning whenever we have a tetrahedron, its two-dimensional faces, meaning the triangles in that tetrahedron, need to be glued along a common segment. And that's really all that we're saying. So I encourage you to draw some sample cases just to get a feel for what the other equations are saying. And you're going to see what happens with the degeneracies there. All right. So this is a very concrete way to deal with simplicial sets. But since we're in an applied category school, let's try to see these structures in a more categorical way. So what is a categorical way to define a simplicial set? We can say a simplicial set is a functor from the category delta up to set. And that's literally all that you need to say. So let's unpack this a little bit. The category delta is the one whose objects are finite order sets. So we denote with brackets n the set that's ordered with elements 0, 1, blah, 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 all the way to n. And the morphisms in delta are going to be order preserving functions. So this is the category delta. And if we take delta up, of course, we keep the same objects and we flip the morphisms around. And a simplicial set is now a functor from delta up to the category of sets. So this is like a classical example of something that we do in category theory where we have this really complicated notion. And when we put it in categorical words, it's like this really short and neat statement. But sometimes you really want to unpack that statement and you want to unpack why is it capturing all that it's supposed to. So let's quickly try to see how is this the same definition that we had before? Like we had a very concrete thing with a bunch of functions and a bunch of equations. So how can you go between the two definitions? Well, the idea is that if we fix an n, we can say that xn in the notion that we had before where we needed to specify a set n. Now, on the other hand, with our categorical definition, this is going to be given by the image under our functor of the object n in delta op, right? So you can, if you start from the functor, you can do x of n and just define your set in the sequence as that. Or the other way around, if you start from the sequence, you can define the functor on objects by taking the corresponding set in the sequence. So this is the correspondence between how the functor is given on objects and what the sets in our sequence are. And we get a similar thing for the maps. So remember, in the very concrete definition, we needed a bunch of base maps di from xn to xn minus 1. And now these, in our functor definition, should be functions from x of n to x of n minus 1. But remember, x is a functor from delta op to set. So this should really be x of some function in delta op, right? And we can define it to be precisely this one. So remember, since we're at delta op, we're going to go the other way. We're going to go from the set n minus 1 in delta to the set n in delta, because the op flips. And this is going to be the function that if we're doing the I, we're going to be identity all the way to I. So we take 0 to 0, 1 to 1, blah, 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 I minus 1 to I minus 1. And then when we get to I, we skip 1 and we send I to I plus 1, I plus 1 to I plus 2, all the way down. So it's the function from n minus 1 to n, whose image does not touch the element I, and it's injective otherwise. So again, we play the same game. If we know who our face map di is over here, we're going to say, okay, we define the image of our functor on this function in delta op as this thing. And if we have our functor completely defined, this is who we set our di to be, right? And we play a similar game for the degeneracy functions, only now the map in delta that we consider is going to go from the set n plus 1 to the set n, and it's going to take 0 to 0, 1 to 1, blah, 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 I to I, and then it repeats 1. So it sends I to I and I plus 1 also to I, and then it keeps I plus 2 to I plus 1, blah, 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 n plus 1 to n. So for the faces, we skip I, and for the degeneracies, we repeat I. That's kind of the deal. Okay, so we can see that from one data, we can determine the other. How do we recover the equations? Well, satisfying the equations on our concrete definition amounts to the functoriality of the x functor that we're creating. So if you start with a functor, you will see that the equations are true because of functoriality. And conversely, if you're trying to define a functor, we do it by the correspondence that we see above, and it will be a functor because of the equations. So that's the idea of how we move between the concrete and the categorical notion. So if you're paying attention very closely, you might wonder, how do we define the functor on the rest of the morphisms in delta op? So if we start with the concrete version, I just taught you how to define the functor on these very specific functions in delta op, the one that skips I and the one that repeats I. But what about all the rest of the functions? How do we define the functor there? Well, this all checks out because of this claim saying any order preserving function can be written as a composite of these functions that skip an I and these functions that repeat an I. So this is kind of a fun combinatorial claim that you can go ahead and prove. But then if we grab any order preserving function and we believe this claim, we write it as a composite of these things, and then we just know how to operate on each of those, and then we compose. And that's how we define the functor in general. All right. So that was our first part about just defining what a simplicial set is and how we like to think about these. So let's now focus on a couple of examples. Now, our first example is going to be the most simple simplicial set that we can consider in a way. And this is what we call the standard simplicial set. So we have one standard simplicial set delta n for each n. And these are defined in the following way. So let me first tell you a sort of pictorial representation when n equals 3. So I should now give you a simplicial set, which is going to be called, like we said, it's going to be called delta 3. And what this means is I should give you a collection of sets delta 3n for n greater and equal than 0. So who are the sets of n simplices for this simplicial set? Well, since we're doing n equals 3, the way that we start constructing this standard simplicial set is by looking at the 3 simplices. So we are living over here right now, and we're going to say we have a unique 3 simplex in our standard simplex. So if we're just thinking of these as sets, we would say, okay, this is a singleton set, whatever. We would just say it's a point. But we really want to keep in mind here our interpretation of looking at these things as higher dimensional triangles. So instead of just saying we have a set with 1 point, we're going to think of it as we have a set with 1 tetrahedron, because this is dimension 3. So we have a unique tetrahedra, and we're going to use it now to determine all of the other simplices by just breaking it apart and taking all the faces. So if we have the tetrahedra 0, 1, 2, 3, now how can we determine all the triangles that we have? Well, we're going to say the only triangles that we have, so the only 2 simplices, are its faces. So we get 4 faces out of this tetrahedra, and that's going to be our set of 2 simplices. Similarly, we're going to break it down in its intervals, and those are going to be our 1 simplices. So if you look at the picture, you get 1, 2, 3, 4, 5, 6 of these. So like the line from 0 to 1, from 1 to 2, to 2 to 3, 1 to 3, 0 to 3, 0 to 2. And those are all of the lines that we have in our tetrahedra. So those are 1 simplices. Our series simplices are the vertices of the tetrahedra. So we have 4 of those, 0, 1, 2, 3. And then what I want to say is that we're done. But again, if you've been paying attention, you might have noticed that we have a problem with degeneracies if we just stop there. Because if this is all the data that I'm giving you, then we would have no problem defining face maps, because face maps are just going to take the faces, and we're considering all the faces, so that would be pretty easy to do. But what happens when I want to put a degeneracy map, for example, from the set of 1 simplices to the set of 2 simplices? Note that since we only took the faces of our really nice tetrahedra as the 2 simplices, in particular, that means we don't have any degenerate 2 simplices. So there's no way to define the degeneracies if this is all that we do. So then what we're going to do is we're going to solve this in the simplest way possible, because really we morally don't want to add any more information. And we're only going to add these degeneracies because we absolutely have to. So then what we're going to do is we're going to say, okay, this information that we see here in the picture is the relevant information. And to each of these sets of n simplices, we add the degeneracies that we get by taking the image of the lower dimensional things. So like since here we want to have an S0 map, we're going to say, okay, to this set of one simplices that we have over here, we're going to add a formal element S0 of 0, S0 of 1, S0 of 2, S0 of 3, and there we go. Now we're allowed to take degeneracies. So this is kind of silly. It's just a formal completion in order for the definition to work, and we repeat everything with all the maps that we're required to get. So following this same idea, we complete our higher simplices, because remember I said we're going to start with the three simplices, but we have higher ones, and we're going to say the higher are all degenerate, only the image by degeneracies of these things that we've accumulated and nothing new. So really this is the relevant information. All right, so I want you to think of this for a moment and really try to see why we call it the standard simplicial set, because we've been trying to use the intuition that simplicial sets have simplices. So this is pretty much like the standard simplicial set delta n is the one that literally has a unique n simplex with our usual meaning of the word, and then breaks it down into its pieces in order for us to have face maps and degeneracies. So in that way is standard. Now, how can we pack all this into a more categorical definition? So this is going to be the same simplicial set, but in a more categorical version. So we want to give a functor from delta up to set, and we're going to say the standard simplicial set delta n is the functor from delta up to set that's represented by the object n of delta up. So remember, a functor that's represented by n simply means we're taking the hom functor in delta. That's the hom functor line, comma, n. So this hom functor is going to take an object in delta up, and it's going to spit out the hom in delta from k to n, which is a set. So that's how we define the functor on objects. And then on morphisms, we should start with a morphism in delta up and give a morphism in set. So if we start with a function f in delta up, which I'm flipping from L to K, the way that we get a morphism between hom from K to N to hom from L to N is to say, well, that's the correspondence that starts with an element here in hom from K to N. That's a function from K to N. And it takes it to the function from L to N that first goes from L to K via F, and then from K to N via G. So it's post-composition. All right. So once again, if we want to define it this way, we might face the question, why are these two things defining the same simplicial set? Like, in our first version, we have tetrahedra and we have pictures and triangles and stuff. And here we have this very formal, this hom functor. How does one version correspond to the other? Well, the way to make the connection is by using this claim that tells us if we define our standard simplicial set in this categorical way, then the non-degenerate K simplices turn out to be precisely the injective maps from K to N in delta. So remember, our simplices are any order-preserving morphism from K to N. And if we want to pick out the ones that are not degenerate, so the ones that we cannot get in the image of any of the degeneracy maps, then these are going to correspond to the injective order preserving maps. So that's a claim that you can go ahead and prove if this sounds like fun. But then there's the more illuminating thing, which is to really check that the injective order preserving maps from K to N are in one-to-one correspondence with the k-dimensional faces of an N tetrahedra. So, for example, here we had 4 two simplices in our example, right? These 4 triangles that we see right here, non-degenerate, I mean. And here we would have to take the injective, order preserving functions from 2 to 3, right? This is K, this is N. So how many injective order preserving functions do we have from 2 to 3? So 2, remember, is the set 0, 1, 2. 3 is the set 0, 1, 2, 3. So let's draw injective order preserving functions. We have the one that takes 0 to 0, 1 to 1, and 2 to 2. Now we can do 0 to 0, 1 to 1, and 2 to 3. Now we can also do 0 to 0, 1 to 2, and 2 to 3. And then finally, we have to move 0. We can do 0 to 1, 1 to 2, and 2 to 3. And now if we want to be order preserving and injective, those are all the possibilities. So we end up with 4 possibilities, each of which encodes one of the triangles that we see here. So if you are better at combinatorics than I am, you should be able to quickly count both of these things and see that they're in one-to-one correspondence. All right, so this is what we call the standard simplex. And the standard simplices provide the intuition for how we think of any simplicial set. Because remember, we said, given any abstract simplicial set, we want to think of their things as n-dimensional triangles. And this is the simplicial set that's literally that. So here, we're not reaching. This is really what we have. And in a way, we are exploiting this specific example to gain intuition for any abstract simplicial set. So you might wonder, why is this a legit thing to do? Like, how arbitrary was our choice of making this example into the one that really represents what's going on in the general case? And the reason why it makes sense to do this is because of the Yoneda lemma. So our dearly beloved Yoneda lemma, let me remind you, tells us that for any functor from C up to set, here C is any category. So for any functor from C up to set, and any object that we fix C in our category C, the Yoneda lemma tells us that there exists a bijection between the set of natural transformations from the Hom functor Hom line C to the functor X. Okay, so that's our first set, natural transformations from this Hom functor represented by the object C to the functor X. And this should be in bijection with the set of elements of X of Z. So X of C is a set because X is a functor from C up to set. And the set X of C should be in a way the same as all the possible natural transformations from this Hom functor to our functor. So that's the beautiful Yoneda lemma. If you haven't seen this before, this has a gazillion applications all over math. It's amazing. But in particular, let's translate it to our setting. Translated to our setting, we would say, for any simplicial set, because those are really the only kind of functors that we care about today, for any simplicial set from delta ob to set. And now we need to fix each object in our category delta, so that's the same as saying each n greater or equal than 0. The United lemma gives us a bijection between the set of morphisms from the standard n simplicial set delta n to our generic simplicial set x, and that's in bijection with the set of n simplices of our simplicial set x. So you can pause the video to really, if you want to, that this is the literal translation of the United lemma to our setting. And this is why we can really think of n simplices of x as the tetrahedra that we use. So the idea, if you want to think of something maybe more familiar, and I'm really bad with analogies, but this is the best that I could come up with. So sometimes when we have a category, just any category, we can probe it because we really like morphisms when we do category theory, right? We're all about the morphisms. So we can probe things to gain information. And in particular, if we have a category and we probe it with the category that's just one object and no maps other than identities, then each of these functors is going to give us an object in our category C. So if we wanted to access the objects, instead of just opening up the category and looking at the objects, we could instead probe it by these diagrams from a point, and each of these probes is going to give us access to one object. So if we follow this kind of reasoning, we can see that this is what we're doing in the case of simplicial sets. So if we want to access the n simplices of a simplicial set, what we do is we probe our simplicial set with the standard n simplex. And each of these probes is going to return an n simplex of our simplicial set. And this is why we think of these as being the image of a tetrahedra, because here we have honest tetrahedra. So the n simplices in X, we think of them as being the picture of a tetrahedra drawn in X, if that makes any sense. Okay, so that was a bit of a mumbo jumbo there. Let's move on to our second example, and this is going to be particularly important for the paper. So our second example is going to be the simplicial set given by the nerve of a category. So given a small category C, its nerve, which we denote by n of C, is the simplicial set whose n simplices are strings of n many composable maps in C. So what does this mean? If we want to know who NC0 is, these are going to be strings of 0 many composable maps in C. So like literally no maps. We just get the set of objects of our category C. For the set of 1 simplices, these are just strings of length 1. So we get the set of morphisms of our category C. For the set of 2 simplices, these are going to be sequences of 2 composable maps in C. So F and G that we're allowed to compose. And then for the 3 simplices, we're going to get F, G, H, which are composable, and so on and so forth. You get the gist. So first of all, how do we interpret these as n-dimensional triangles? Remember, we said that's something that we always want to do. Well, for NC0, which are the objects of C, we want to see these as vertices, which is really easy. Just picture the objects as points, which you see as vertices, right? For NC1, we want to see a morphism in C as an interval. Again, that's really easy. It's pretty much how we draw morphisms anyway. But then it gets a bit more interesting because for NC2, what we get from the nerve definition above is just two composable maps F and G. And we want to think of these as a triangle. So you see that there's a side missing in our triangle. And what we do is we fill that triangle with a composite, GF, which we can always do. No big deal. We're really not doing anything here. For dimension 3, it gets even more interesting because now, let me just erase the fillers to get a clearer picture. Now, according to our definition, we're going to start with three composable maps, F, G, and H. And we want to picture these as the data of a tetrahedron. So first, we fill in each triangle face. If we look at FG, that gives us a way to fill this triangle with GF, just like we did before. If we look at GH, we can fill this missing side here with their composite. And now we have to fill a remaining line in our tetrahedra. But now we have choices. If we look at the back face in the tetrahedra involving the vertices A, B, and D, then we would say, okay, we're going to fill this line to be first do F and then do the composite HG. But instead, if we look at the bottom face of the tetrahedra, which is the one involving the vertices A, C, D, we would say, oh no, you want to fill this as first do GF and then do H. But of course, since we're living in a category and composition is associative, this is really a non-issue because these two options are the same. So we see that we have a unique way to think about each of these strings of composable maps as the corresponding n-dimensional triangle. So that's the nerve in our usual way to think of simplicial sets. And there's a bonus here because not only is this N of C construction a simplicial set, but actually this assembles into what we call the nerve functor. So it assembles into a functor from CAT to the category of simplicial sets, which of course picks out a category and spits out the nerve. And this nerve functor is fully faithful, which in practice is really, really good because it means that we can view categories as embedded into simplicial sets. So like for all intents and purposes, if we want to study categories, we can just think of them as being simplicial sets through their nerve and then just do stuff as simplicial set, which have a really nice combinatorial feeling to them. Okay, so these are the two examples that I'm going to talk about today. And of course, there's thousands more that are super important and I'm completely, utterly ignoring. So please Google simplicial sets if this is something that sounds interesting to you, because as an algebraic topologist, I must say they're super, super cool. Please ask me any question that you have about simplicial sets, and I would love to talk about them more. But now let's move on to our final section, which is a small conversation on segal maps. And this might be newer to some of you because this is really a much more homotopical notion. All right, so what are these segal maps? The idea is that through example 2, we saw that we can grab a category and take its nerve and construct the simplicial set. And since this embedding, like we said, is fully faithful, we know that some simplicial sets are categories in the sense that they're the nerve of some small category. Okay, so some simplicial sets come from categories, but a natural question will be, how can we recognize them? Meaning, if I give you a simplicial set X, how can you tell me whether that simplicial set X is isomorphic to the nerve of some category or not? And the answer to this question is by looking at the segal maps. So let's define these segal maps. Given a simplicial set X, we're going to create a picture for each n greater or equal than 2 and each k bigger than 0 and smaller or equal than n. Okay, so here is the picture that we create. On the bottom, we are going to have n plus 1 many copies of x0. We're going to have n copies of x1. And then from each x1, we project to 2 x0s via the faces, right? So given an x1, we can take its d1 face and go to x0, or we can take its d0 face and go to another x0. And then we form this zigzag of x1s and x0s by doing this. This is our blue picture right here. And now on top of this picture, as the apex, we're going to put xn, the set of n simplices. And xn is going to have one map to each of the x1s. And the map to the first copy of x1 is going to pick out this one simplex in xn, which goes from vertex 0 to vertex 1. Then we're going to have a morphism from xn to the second copy of x1, which is going to pick out the one simplices joining the vertices 1 and 2. And so on and so forth until the very last one, which goes from xn to the last copy we have of x1 that picks out all the simplices from n minus 1 to n. So once we form this picture, for a moment, we're going to forget about the xn part, and we're only going to look at our zigzag between x0s and x1, and we're going to take the limit of that diagram. So that's like a mixed pullback. You take a pullback and then another pullback and then the pullback of the pullback, and you do that until you only have one thing left. And if we denote the limit of that blue part of the diagram by just this x1 cross x0 cross x0 cross x1, then we know by the universal property of the limits that there exists a unique map from the apex of the picture that we constructed, which is xn, to the limit. That's literally the universal property of the limit. And this unique map from xn to this limit is what's called the segal map. Okay, so that's a lot. That was a lot. Let me unpack what this map is for dimension n equals 2. And really everything's going to click together. So let's just deal with the case n equals 2. We have the picture x0, x1, x0, x1, x0. That's our zigzag picture. So what are the faces doing? Remember, if we start with an element in x1, we think of this as an interval from 0 to 1. Then the d1 face gives you 0, and the d0 face gives you 1. So this is what the zigzag is doing. What does it mean to take the limit of the zigzag? Taking the limit means picking out the pairs of one simplices which share a common vertex. So it's like you can do one segment and then the other, and they're glued on the vertex on the middle. So that's exactly what the limit is. And now the segal map is going to be a map from x2 to this thing. And remember, x2 were the triangles. So what this map is going to do is it's going to grab a triangle 0, 1, 2, and it's going to pick out the two segments that share a vertex. And if we think of these triangles as being directed, so think of these things as having a direction, that's always order preserving. So you go from 0 to 1, from 1 to 2, and from 0 to 2. Then in this directed picture, there's really only two segments that you can do one and then the other, and those are 0 to 1 and 1 to 2. And that is exactly what the segal map is doing. The segal map is grabbing a simplex and picking out the spine of the composable intervals. Alrighty. So remember, we wanted to use these segal maps to identify which simplicial sets were nerves of categories. And here is our first wonderful claim. When our simplicial set X is the nerve of a category, this segal map S2 that we just described is an isomorphism. And this is actually quite easy to see, because how would you go the other way? You start with a pair of two composable functions in your category, right? Because remember, if this is a nerve, then the 0 simplices are objects. We have A, B, C. The 1 simplices are morphisms. So we have two morphisms, F from A to B, G from B to C. And that's our limit. It just means you can do F and then G. Now we want to build a map that goes from here to a triangle. But remember that we said, how do we create triangles? We just do the filler with a composite. We don't even need to do the filler if we don't want to, because the filler is uniquely determined by the F and G part. So this is obviously an isomorphism. And the reason, like we said, is because in C we have a unique composite of F and G. The word unique here might seem a little silly, like, of course, we have a unique composite. What does that even mean? I just want to stress this because in more topological scenarios, we might have different choices of composites, but that's never the case when we're dealing with categories. So we can go higher and in fact show that if we are the nerve of a category, then S3 is also an isomorphism. S3 is now going to be the third segal map, and it's going to pick out composites of 3 maps. And if you draw the picture, and I highly suggest that you do, you should quickly see that the reason why S3 is also an isomorphism is because composition in our category is associative. This is really similar to the story that we were doing when we were creating the fillers to see the nerve as the triangles, and we were finding that there's really only one possible way of creating the filler. This is exactly what we're seeing here in the segal maps being isomorphisms. All right, so if we come from a category as the segal 2 map is an isomorphism, the segal 3 map is an isomorphism, but in fact, there's this wonderful thing that we can do if you just stare at the definitions for a while. You can see that a simplicial set is isomorphic to the nerve of a category if and only if all the segal maps are isomorphisms. So looking at the segal maps is a way of completely answering the question, does my simplicial set come from a category or not? All you have to do is study the segal maps and check whether they're isomorphisms or not. So that's pretty sweet, and it gives you a really good idea of how segal maps encode composites and the way that composites behave, and they're being associative or not. And this should plant the seed for some things that we're going to be looking at in the paper. So a final word is that all that I did today was talk about simplicial sets, which were functors from delta op to set. But one can pretty much consider simplicial anything. So one defines in general a simplicial object in a category C as a functor from delta op to C, and then pretty much all the things that we did here for set, we could do for a general category C. So in the literature, when you fix C equal to the category of sets, you get simplicial sets like we did today. You can also fix C to be the category of topological spaces, and you get simplicial spaces. These are really used in algebraic topology. You can fix C to be the category of categories in functors and get a simplicial object in CAD. Unfortunately, we were historically a little bit dumb, and the term simplicial categories, which is what you would naturally want to name this, is already taken and it means something else. But you can play this game of picking different categories and looking at simplicial objects in them. And it gives you a good way to access the category, and you build these combinatorial structures on the category, which are super interesting. All right, so I will post the notes, and please feel free to reach out if you have any questions.